Welcome students to Production Classes as PSC, and today we are going to discuss about an important application of Gauss's theorem. And for the previous class I just completed up to the what is Gauss's theorem, what is area vector, what is solid angle, and how what is the relations between the charge and the luminous flux. There is flux and also the electrical flux. And for today's class we are just discuss about the application of Gauss's theorem, that is for surface distribution of charge. So students, take a heading, application of Gauss's theorem, application of Gauss's theorem. Application of Gauss's theorem, and this is for surface distribution of charge. Surface distribution of charge. So students, first of all, you have to know what is surface distribution of charge, and I just discuss for the previous class, but today I again repeat. If there is a you can take a particular surface like a seat, so if that particular seat contain charge and all the charges are distributed uniformly, then you can say that the surface density of charge sigma equal to total surface, total charge divided by total surface. So if we take a small surface element, if we take a small surface element, then we can write dq by ds, dq by ds, but the density remains same. Such as if you sip a small amount from a cup of tea, then you can feel what is the meaning of density, that it's you can feel your sweetness from all the sips. Okay, so dq by ds means the charge density. If we take a small amount like that, then you get that this portion contains this coulomb by meter square surface density, and if you take here a small portion, then you also get that value remains same, that is sigma equal to q by s. So there is a surface distribution of charge, and you have to calculate electric field at somewhere due to this distribution of charge. But particularly you cannot apply Coulomb's law, students, because Coulomb's law states that if there is a charge, then it can create a field, and at a particular point you can get this field as 1 by 4 pi epsilon naught q by r square. That is only applicable for a point charge. When a charge is remain at a particular constant at a particular distance, and you have to calculate electric field at some proper distance, suppose it is r from these charges, then at that point electric field is 1 by 4 pi epsilon naught q by r square. But students, for that one, for that distribution of charge, if the charge are distributed within a space, then how we can calculate electric field at some distance? Then you have to apply Gauss's theorem. So this is the application of Gauss's theorem, and I discussed for the previous class for linear distribution of charge, it will be E equal to kappa 2 lambda by R. And what will be that for the plane sheet, for a distributed charge distributed over plane sheet? So you can take this as infinitely long, infinitely extended, and you can think like uh, that particular roof as infinitely extended. And actually finite and infinite are so relative term. If we consider this surface and we take a small portion, then we can compare this one with respect to the total surface that is infinitely extended. So a small portion is taken and it is infinitely extended. That's why you can represent like that. So you have to calculate electric field at that point, suppose. Then first of all, you have to consider a Gaussian surface. What is Gaussian surface? Because students, Gauss's theorem states that phi net equal to q by epsilon naught, and the Gauss's theorem you apply only for that case when the charge is enclosed within a surface. So first of all, students, you have to enclose that particular one. Suppose a bed sheet is given and something is put on the bed sheet, and I say you that please cover it. Then you can take a help of a glass tumbler and you can press over it. So like that, if we wanted to cover this charge, then we use like a glass tumbler or cylindrical surface. Cylindrical surface. So this is the cylindrical surface, and what is the, first of all you have to know, this is a sheet. This is a sheet. So for that particular sheet, the charge are uniformly distributed over a particular layer. It is not a plate. If plate is given, then the charge remains at the two surfaces, that is here and that particular surface. So you can calculate electric field like here, like within the medium, within that particular two sheets, and you can calculate also electric field for the left side, right, and for the center of the, that is between the two sheets. So surface distribution of charge, at least we know that what is surface distribution of charge when charge distributed over a surface area. If it is linearly distributed, then along a particular line, then you have to take lambda equal to q by total line. If surface is given, then you have to take sigma, that is surface density of charge, that is q by total surface area, or you can take a small portion divided by the small portion, that charge content within the small portion divided by a surface area of that particular portion, and the unit is coulomb by meter square. Okay. So applying Gauss's theorem, you have to calculate electric field intensity at somewhere from that particular sheet. So if we want to cover that particular charge, suppose students, there is a charge here and you have to cover it, then you just like that cylindrical ones, and you have if there is a charge and you have to cover it, then you can take with the help of this, you can cover like that. But if this is a plate, but when this is a sheet, then if I cover it like that, then charge, there is the effect of the charge, that is here electrical field lines generated for both the sides. So if we cover it like that, then the electric fields are penetrate and generate along that particular direction. So you have to take like that one, that is you have to cover that particular surfaces like this. So you have to take two cylinders like that and cover these charges like that ones that is shown in the figure. Okay, students. So here the electric field lines are penetrate this surface like that, and also from the back side it is penetrate like that box. So this is an imaginary surface. You can imagine like that. This is a sheet, and you can imagine that there is a cylindrical closed surface, and within that particular cylindrical surface there is a charge. And if you take this particular area as suppose this is ds. This is ds, and it is infinitely extended. You can take this one as a or not. You think it. If we take a small surface, then you must take it as ds, since d signifies a small area. D signifies a small area. So this is a small area, and if we imagine that this is the cylinder, then you can take A is the area. A is the area of that particular cylinder. But that particular, for the sheet of paper, you have to imagine here that is the sheet of most of the books use A. And if we consider this one is A, then this one is also A. And what is about the total sheet? So you have to take a small area ds, or ds vector equal to the magnitude into n cap, that is the unit outward normal along this direction. That is n cap is along that particular direction. And since electric field is also a vector quantity, then for the electric field, if we take it is a vector quantity, then E into, if we take r cap is as the outward normal, then r cap is that one. So r cap dot n cap makes an angle of 0 degree. So r dot n cap dot n cap, and this is equal to 1 here. But if we take a small portion of area on the curved surface, and I discussed that a cylinder has three surfaces. One is circular on the upper side, and the bottom is also pi r square, and this one is 2 pi r h. So it consists of three surfaces. So when we take a closed surface integration of electric field, then you have to divide it into three integral parts. That is, for the two surfaces you have to take two integral, and for the curved surfaces you have to take another integration. So this one is 1, and this is 2, and this is 3. So there are three surfaces actually. This is a Gaussian surface that covered that particular charge, and if it is the charge is not enclosed, then we cannot apply Gauss's theorem. So for applications of Gauss's theorem, first of all, this is a sheet, and all the charges are distributed uniformly. When the charges are distributed uniformly, then you can take only a sigma equal to total charge, or dq by ds. Total that small element and the charge content within that particular element. So if we take a small area over here, then the outward normal is along this direction, but still electric field acts along this direction. That is, we can take it is as r cap. And if we take that particular one along this direction, then this is also suppose n cap or minus n cap. It may be minus n cap, since this is the directions of n cap, so this is n minus n cap. But electric field is act along that particular direction, and it is minus of r cap. You can take since the electric field acts along that particular direction. For positive charge it is outward direction, for that positive it is also that is the outward direction. That is, you can take it as minus r cap. since electric field is a field or a space vector, then you can take that electric field is generated along all the directions. For both that particular say it is directed for the outward direction, that is along the right side and along the left side. Okay, so let's what is Gauss's theorem, and again memorized that phi net means if a charge is contained within a closed surface, then phi, the flux generated, flux, that is number of electric lines of force, and this is closed integration of E dot ds. Closed integration means these particular charge, these all the charges are contained within a cylinder. So this is equal to Q inside, it may be dq. Q inside means the charge contained within that particular cylinder. So if we take this is dq charge is remain here, so here we can write dq by epsilon naught, So phi net equal to E dot ds, this is equal to dq by epsilon naught. And students, we divided this or separate the three integral values, that is integration, and you must have write that it is open integration, this is closed integration. And so open integration of one number surface, that is for that particular surface, you have to integrate this one E dot ds, plus integration for the two surface, second number surface, is also take E dot ds, and for the third surface you have to take E dot ds, and all are the open integration. Only for that particular case, if we divided the cylinder as surface 1, surface 2 and surface 3, then you have to break up this total closed integration as open integration. So this is equal to dq, or dq equals to sigma into ds. So sigma ds by epsilon naught. So sigma ds by epsilon naught, and for that one E dot ds, n cap and r cap acts along this direction. So n cap dot r cap, or minus it may be, this is equal to 1. So this integration exists. Plus this is the integration, plus integration 2 is 0. Integration 2 is 0 since this is angle of 90 degree. So n cap dot r cap equal to, students, this is 90 means 0 cos 90 degree. So for the third one E dot ds or eds, we can write eds, and more sincerely you have to done it, because when you write down that is electric dot ds equal to E dot eds, this is the vector, this is the magnitude. So here eds cos 0 degree, that is 1, so that's why we can write eds. This is equal to sigma ds by epsilon naught. Or if we student integrate this one, first of all I say that if sigma equal to total charge by total area, suppose total area is S, that is that for that particular sheet extended, then this one is this. So that for that, if we consider for that particular one, then E dot ds, that means eds, or ds, integration of ds means total surface. So total surface means the sheet is extended over here. So for eds, then es, for that particular case it is also es, and this is equal to sigma into ds. For the students, we can write here that if dq is taken, then it is sigma ds, and if whole surface is taken, then for that charge then transfer into a q. So this is sigma s. So sigma s means total charge, and if we take all the integration, then you have to take this integration. What that is for the total surface area. So for we can write here that sigma is by epsilon naught. Sigma is by epsilon naught. So ES and ES that turns into 2ES. That is 2ES equal to sigma S by epsilon naught, or S cancel this one. So electric field equal to sigma by 2 epsilon naught. So electric field equal to sigma by 2 epsilon naught. Now the question is that is this electric field is a function of R or not? This electric field is a function or not? And most of all students, I repeat again, most of the book take is as Q. So if we placed here as Q, then you have to integrate that particular surface. So when we take closed integration of E dot ds, suppose you write that E dot ds, and if we take a integration, then you have to integrate all the charge. You have to integrate all the charge. So I think it will be better for integrate this one, that is you have to write here as total surface. So it will be better, because we integrate this one first of all from the initial time. So you have to take integration of dq or summation of dq. Summation of dq means that is all the charges contained within the total surface, total sheet. So there is summation of dq. You can write integration of dq, or you can write summation of dq. So integration of dq means the total charge equal to sigma. So that's why here you can write dq equal to sigma is by epsilon naught. That is this is the final result. So here you can also write yes. Okay. So electric field equal to sigma by 2 epsilon naught. That is the electric field at a particular, here the electric field is sigma by 2 epsilon naught. Okay. And if we take at a particular point P, then also electric field is sigma by 2 epsilon. Now the question is that is this electric field is not a function of R? That is, when we are away from that particular sheet, then the electric field is changing or not. Let's take a questions. So students, when we consider this particular sheet, and it is the surface distribution of charge over here, and if we calculate electric field at that particular point, then you can write sigma by 2 epsilon naught along this direction. So if you take this as a vector, then you can write here as n cap, and if you take this one as this along this direction, then it will also electric field equal to sigma by 2 epsilon naught, that is minus n cap. Okay. So electric field at that particular point is this one, but the electric field is at that particular point E is sigma by 2 epsilon naught into n cap. It is also the same, because it doesn't, that density doesn't change, and epsilon naught is a fixed value, that is 8.85 into 10 to the power minus 12. Suppose students, there is a bulb, and if you go away from that particular bulb, then I questions you that is that particular intensity changes or not, then you easily say that yes, why not? So again this is like a questions, the sheet is given here, and if we move away from that particular sheet, then the electric field is changes or not. If yes, then it must be a function of R. E must be E, then electric field must be a function of R. Electric field must be a function of R. Since for the first applications we know that if a linear distributed charge is given and you have to calculate electric field, then it is kappa and 2 lambda by R. 2 lambda by R. So electric field is a function of R. That means if you move away from that particular linear distribution of charge, then electric field decreases. But for that particular one, electric field is not the function of R. That's why we can say that electric field doesn't change. But why electric field doesn't change? Because the students, suppose this is the Earth surface and you take a flight from here. When you stay at that particular position, then your field of view is like that. You think that when I standing here, then I can only see that particular space. But if we on the roof of this particular house, then we can see a wider range of view. So students, when the location is this, at that particular location, that is the observation point is here, then that particular boy can see a charge like an area this one, and if the boy is here, then he see a charge of like a wider region. So at that particular point, contribution of electric field is only for that particular charge. And if he is at that particular position, then the contribution of this charge is for that particular point. So electric field decreases. Yes, electric field decreases, but the more and more charge can compensate that particular decrease in electric field. Yes. So this is the fact, and it is more interesting. So when the observation point is away from the seat, more and more charge are coming into the field of view that compensate the decrease in electric field due to the that particular observation point when moving away from the seat. So this is that's why it is not a function of R. So next we can apply this particular concept into different cases. Suppose take case number 1, students. Case number 1. Suppose there is a seat that is plus sigma, and there is another seat of charge distribution plus sigma. You can modify it like that one. So this is a seat of charge contents, here is plus sigma, and this is also a seat that contains also the same charge distribution. Plus sigma means same charge distribution. So student, if I say that this is 1 and this is 2, for the one plate, for plate number 1, if we want to calculate the electric field intensity at that point, then you can say that this is for 1, it is sigma by 2 epsilon naught. It is sigma by 2 epsilon naught, because for each plate the electric field is sigma by 2 epsilon naught. It will be better if we change the board and take different pencils, then it will be more better. So students, first of all, I change the board and take that particular board on the opposite side. So this will be you can realize that particular concept more clearly. Okay. So student, take a seat like this is a seat. and it contains this is over a smooth surface, so the reflection of light is actually greater. That's why the focus continuously changes due to the exposure, I think. So I prefer to use a comparatively rough surface. So this is another sheet of same charge distribution. Same charge distribution. Yes, same charge distribution. And if we consider that particular one, then at that point, the electric field E equal to sigma by 2 epsilon naught. Sigma by 2 epsilon naught and acts along this direction. Then if we take it as a vector quantity, then you can take this is n cap. N cap. And if we take for that one, then it is also sigma by 2 epsilon naught. And this is also E vector equal to sigma by 2 epsilon naught, and this is along n cap. Since electric field is not a function of R. Again, students, if we take at that particular point due to the positive one, then it is directed along this direction, and if we take for that one, then it is directed along this direction. Why? Because for positive charge, the field lines is always in the outward direction. So it is so simple. You stand here like that and stretch your hand. It is a simple rule. You stand here and stretch your hand like that. Then you can realize the particular direction. So stretch here. Okay, this is the simplest rule, and so you compare this portion, you compare this arrow and this arrow at that particular portion. You can compare here like that, and for that particular point, there is it is center, and it is right side, and it is left side. So at the left side, for that particular charge distribution, it is also outward direction, and for that one it is also outward direction. I think you realize that one. What is sheet? A sheet is a distributed charge, and what is the value of electric field for that particular sheet? When two sheet is given, that is on the right side, that is on the left side, and that is for the center. So for the left side, it is also sigma by 2 epsilon naught, and this is minus n cap, and this is sigma by 2 epsilon naught, and this is also minus n cap, and this is also sigma by epsilon naught. So these and the others, since the electric field is same, so here the electric field is 0. At the center. At the center, you can write E suffix C. Electric field is 0, but on the right side electric field, and this is equal to this plus this. So sigma by 2 epsilon naught plus sigma by 2 epsilon naught, and this is along n cap. So this is half plus half, that is 1. So sigma by epsilon naught into n cap is the electric field at the right side, and you can write it as a vectorial notation. So at the left side, it is electric field left equal to sigma by epsilon naught, and this will be minus n cap. So I think student, you realize that for the distribution of charge, that is two sheets, when two sheets are taken, then you have to calculate electric field at the center, at the right side of the sheet, and at the left side of the sheet. And you can combine these numericals with different concepts. These are the main tricks to clear that concept easily. When positive distribution of seats are given, then stand below that seat and take and stretch your hands. Okay, so this is also a sigma plus sigma, and this is this will be better for color complications, and you know that very clearly. So this is negative. Negative means it is always directed in the towards the charge. So negative charge means electric field lines act along that particular direction. So for the negative ones, the direction is always, and you can think the arrow the arrow always attack minus sigma, and when plus is given, then all the arrows are away from this one, away from that positive distribution of charge. So this is the, and each arrow contribute sigma by 2 epsilon naught. Magnitude of electric field for each arrow is sigma by 2 epsilon naught. So that for that one, this is equal to this one, so electric field is 0. And this one is also in oppositely directed, so electric field is 0. But at that particular case, electric field is equal to sigma by 2 epsilon naught, and it is along a particular direction. That is n cap. That is n cap. Okay. So when plus, and if we take another example, suppose this is like this, it is a different case. That is when plus and minus sigma is given, and if we take the two as minus sigma, and this is also minus sigma. We can take it as another combination. There is minus sigma, and for that minus sigma, the arrow is along this direction, along all the arrows attack minus q. And for negative, it is also along this direction, since this is negative, so that particular one is also directed towards that minus sigma. So then you can judge that one, that is, this is along this direction, so the electric field is sigma by epsilon naught into minus of n cap. Minus means along this direction, and this is E vector equal to sigma by epsilon naught, and it is directed along n cap, and for that one, it is the center, the electric field is 0. So these are all the case that the question is that the electric the density of the charge, if the density of the charge is uniformly distributed, but the two plates are not equally charged, uniformly charge always resides on the surface uniformly. So for that one, we can consider that when the distribution is sigma 1, and this is sigma 2, and this is sigma 2. So this is I think this is all are positive, and if negative, if one is negative and one is positive, so the for that one, the direction is more vital. For plus sigma 1, the electric field at that point, electric field at the center directed along this direction, and along this direction, and along this direction. So that is the rule. Stand here and stretch your hand. Stand here and stretch your hand. So all the arrows within the left side are along this direction. All the arrows in the right side are along this direction. Okay. So for sigma 2 and sigma 2, for sigma 2, it is also stand here and stretch your hand. So this is minus, and this is also along this direction. So this is also along this direction. And take plus sigma. Plus sigma means sigma 1 by 2 epsilon naught into n cap. So cap is more vital. Here sigma 1 into 2 epsilon naught and n cap. Cap is more vital. and this is also sigma 1 by 2 epsilon naught, and cap is more vital, but this, if since this is n cap, so this is minus n cap, because this is the left side and this is the right side. Okay, so for that particular charge, and this is also sigma 2 by 2 epsilon naught, and this is n cap, and this is sigma 2 by 2 epsilon naught, and this is minus n cap, and this is sigma 2 by 2 epsilon naught, and this is also minus n cap. So now students, you have to take a vectorial addition. Why this vectorial addition? Since electric field is a vector. Since electric field is a vector, then you have to take a vectorial addition. That is, for this one, E equal to electric field, net electric field is equal to E1 plus E2. So E1 means this is sigma by 2 epsilon naught, sigma 1 by 2 epsilon naught plus sigma 2 by 2 epsilon naught, and this is along n. So if sigma 1 and sigma 2 are the two densities of charges given, then you put here and get that result. And for that one, and you have to know that electric field at the center, and this is equal to sigma 1 2 epsilon naught n cap plus sigma 2 by 2 epsilon naught into minus n cap. So if sigma 1 is greater than sigma 2, the density of sigma 1 is greater than this one, then the resultant direction will be along n cap. And if sigma 2 is greater than sigma 1, then the resultant will be along minus n cap. So this arrow leads when sigma 1 is greater than sigma 2, then you have to take n cap. And if sigma 2 is greater than sigma 1, then you have to take minus n cap as a final direction of the electric field. And for that one, you can calculate it. This is left. This is, suppose for that viewers, if we take this is right and this is center and this is left, so left equal to electric field left equal to sigma 1 by 2 epsilon naught into minus n cap plus sigma 2 by 2 epsilon naught into minus n cap. So this is a simple case like that, and you have to add this one, sigma 1 by 2 epsilon naught plus sigma 2 by epsilon naught, and then minus n cap. So the direction will be along that particular direction. So these are the different cases that when a charge is distributed over a surface area, then you have to take sigma as a surface density of charge, and I repeat again, sigma equal to total charge by total surface area. So total charge means coulombs by surface area meter square, so the unit of sigma is coulomb by meter square. And the electric field you have to calculate like that. And for the next class, I discuss about different numerical concepts, and all the numericals are taken from IIT or it means joints, main or NEET, and for the you can take for the different examples at the previous NEET exams. You can take the previous year all the questions, and also you can take a conceptual. Most vital is concept is clear or not. So when your concept is clear, then all the questions you can solve it. So you have to think knowledge and experience. Knowledge and experience, or feelings. If you clear the concepts but the feelings is not, then you cannot solve all the questions more sincerely. But if knowledge and feelings recombined and combine that one, then you can easily crack that particular exam. Okay students, so first of all, feel the concept and realize, and your realization is will be more. Okay, so for today's this is the last concept, and for the next class I take the another applications, that is it may be a spherical distribution of charge, that is volume distribution of charge. It is for the spherical cell, or it is a solid sphere. It is a solid sphere. And then you can take like hollow like structure, like when the charge is distributed for that small portion, and you have to calculate electric field here, electric field here, electric field here. And you can take also a cylindrical portion like that, and you have to calculate. And if the cylinder is like that one, then what is the difference between the linear charge and this particular cylinder? And if we take a like structure and the charge is given over here, and you have to calculate electric field within that particular region, then what is the value of electric field for that particular region? And another different concepts like symmetry. By symmetric rule, if a charge is given at a spherical like hemisphere, then what is the net flux? That will be Q by epsilon naught, or half of Q by epsilon naught. That is the symmetry argument. And you can also follow the AC Burma series, and I think that the electrostatic, for that electrostatical portion I completed up to still now up to 30 and above numericals, 31 most probably, 31, and the total numericals is about 87, I think. It is not clear for me. And then we can complete a Gauss's theorem, and so you can also follow that portion, the Gauss's theorem, from numerical 1 to something, it may be 80. So most of all you have to follow the Erudov series and AC Burma series, as well as for numericals. This is mainly a conceptual and numerical channel. So when you feel your numerical isn't clear for that, then you can follow that particular channel. Okay, so thank you, and subscribe and keep studying. Okay.